Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is series and parallel arrangements of capacitors. Our objective is to examine the details of the charge process for series and parallel arrangements of capacitors. As you recall from the capacitors lecture, available at the Big Bad Tech channel, we learned to calculate the total capacitance of series and parallel arrangements of capacitors. The process was easy enough if you could remember this simple rule. Do the opposite you would do if calculating resistors in series and parallel. To calculate the total capacitance of a series arrangement of two capacitors C1 and C2, multiply C1 times C2 and divide it by C1 plus C2. If you're presented with a series combination of 3 or more capacitors, 1 over the total capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3, and so on. Finally, if you're presented with a parallel combination of capacitors, total capacitance is equal to C1 plus C2 plus C3, and so on. Lumping a series or parallel arrangement of capacitors into a single total capacitance is an effective, yet kind of superficial means of circuit analysis. Today we'll look at the dirty details of the individual capacitors making up the total capacitance. As a preparatory exercise to this discussion, I present you with this challenge. Consider this circuit consisting of a 30-volt DC source, an open switch that closes at t equals 0, R1 a 200 ohm resistor, R2 a 500 ohm resistor, and R3 a 400 ohm resistor, and a box with the word 20 microfarads written on the outside. We're unaware if this is a single 20 microfarad capacitor, two 10 microfarad capacitors in parallel, a 12 and an 8 microfarad capacitor in parallel, two 40 microfarad capacitors in series, or a 30 microfarad and a 60 microfarad capacitor in series, or some other combination of capacitors that results in a total capacitance value of 20 microfarads. All we know, the element in the box has a total capacitance of 20 microfarads. What's great about this assumption is this. You are hereby authorized to treat whatever is inside the box as a single 20 microfarad capacitor. Don't make the analysis of series and parallel capacitors hard. Treat whatever arrangement you're presented with as a total capacitance and then figure out the inner details later. Therefore, our first challenge is to see how this 20 microfarad box undergoes the charge process as if it was a single 20 microfarad capacitor. Let's assume this 20 microfarad element in question is initially uncharged, i.e. it has initial voltage of 0 volts. Analysis of this type of charging circuit is a skill you've had ample experience with by now. As such, I leave it to you as an exercise. If you need a task list, here it is. Determine the Thevenin's equivalent circuit seen by the initially uncharged capacitor. Determine the time constant for the charging process. Determine the initial conditions for the capacitor. Determine the final conditions for the capacitor. Determine the time-varying expressions for voltage across the capacitor and current through the capacitor. And finally, draw plots of voltage across the capacitor and current through the capacitor for a full charge of 5 time constants. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following data. The Thevenin's equivalent circuit seen by the initially uncharged capacitor is a 15.8 volt DC source in series with a 105.3 ohm resistor. The time constant for the Thevenin's equivalent circuit is roughly 2.1 milliseconds. At t equals 0, voltage across the initially uncharged capacitor is 0 volts. This means 15.8 volts appears across the Thevenin's equivalent resistor at the onset of the charging process. An application of Ohm's law demonstrates that the capacitor would experience an initial surge of 150 milliamperes. After 5 time constants, in this case 5 times 2.1 milliseconds, or 10.5 milliseconds, the fully charged capacitor will experience a 15.8 volt differential. Current through the fully charged capacitor will be 0 amps. Current through the capacitor as a function of time could be modeled as IC of t equals 150 milliamperes times e to the negative t over 2.1 milliseconds, where 150 milliamperes is the magnitude of the initial current surge and 2.1 milliseconds is the time constant. The plot of current through the capacitor as a function of time demonstrates it spikes at 150 milliamperes and then drops to 0 by 5 time constants or 10.5 milliseconds. Voltage across the capacitor as a function of time could be modeled as Vc of t equals 15.8 volts times 1 minus e to the negative t over 2.1 milliseconds, where 15.8 volts is the final voltage and 2.1 milliseconds is the time constant. The plot of voltage across the capacitor as a function of time demonstrates it starts at 0 volts and grows to 15.8 volts by 10.5 milliseconds. Using these plots and time-varying expressions, one could solve for electrical properties at specific times and solve for time values that satisfy specific conditions. As an exercise to the viewer, I invite you to solve for the instantaneous voltage across the capacitor and current through the capacitor at t equals 1.5 milliseconds just a little before one time constant into the charge process. Additionally, see if you can solve for the time voltage across the capacitor reaches 12 volts. At the same time, determine the instantaneous current through the capacitor. Note if you've been following this lecture series in its intended sequence, by now you've had ample experience solving for instantaneous values at specific times and solving for specific times that satisfy given conditions. As such, I'm kind of cutting you loose. From this point forward, I will not be spending further time detailing the algebraic processes to obtain these results. From here on out, you are on your own. If you're struggling with this process, by all means revisit and review the exponential functions lecture, available at the Big Bad Tech channel. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following data. At 1.5 milliseconds, voltage across the capacitor is roughly 8 volts, and current through the capacitor is roughly 73.6 milliamperes. At t equals roughly 3 milliseconds, voltage across the capacitor is 12 volts, and current through the capacitor would be 36 milliamperes. Thus concludes the transient analysis of the charging process for our total capacitance. In summary, at t equals 0, voltage across the initially uncharged capacitor is 0 volts, and current through the capacitor is 150 milliamperes. At 1.5 milliseconds, voltage across the capacitor is roughly 8 volts, and current through the capacitor is roughly 73.6 milliamperes. At t equals roughly 3 milliseconds, voltage across the capacitor is 12 volts, and current through the capacitor is 36 milliamperes. Finally, at 10.5 milliseconds, voltage across the fully charged capacitor is roughly 15.8 volts, and current through the capacitor is 0 milliamperes. Between t equals 0 and 10.5 milliseconds, current through the capacitor as a function of time could be modeled as IC of t equals 150 milliamperes times e to the negative t over 2.1 milliseconds, and voltage across the capacitor as a function of time could be modeled as Vc of t equals 15.8 volts times 1 minus e to the negative t over 2.1 milliseconds. Make a note of these instantaneous values and time-varying expressions, as they'll be useful references later in this lecture. Let's now explore the details of this lecture's intended topic, notably series and parallel arrangements of capacitors. Given the element or elements inside the box have a total capacitance of 20 microfarads, we're presented with 5 options, 3 of which are stupidly simple, and 2 of which necessitate a little thought. Option 1, the easiest of all options, the element inside the box really is a single 20 microfarad capacitor. All our previous analyses and results hold true. Cut, paste, problem solved. Option 2, also super easy. The elements inside the box are a parallel arrangement of identical capacitors that happens to yield a total capacitance of 20 microfarads. Consider a parallel arrangement of 2 10 microfarad capacitors yielding a total capacitance of 20 microfarads. Voltage across elements in parallel is the same. At t equals 0, both capacitors are initially uncharged at 0 volts. By 1.5 milliseconds, both capacitors will have been charged up to roughly 8 volts. By roughly 3 milliseconds, both capacitors will have charged up to 12 volts. And finally, at t equals 10.5 milliseconds, the end of the charging process, both capacitors will have been fully charged up to 15.8 volts. Let's now examine how current flows through this parallel arrangement of identical capacitors. Given these identical capacitors present essentially equally sized vessels for charge storage, charge current will split into 2 equal paths, half at any time going to C1, the other half going into C2. At t equals 0, the initial current surge of 150 milliamperes splits into 2 equal paths. Half of 150, or 75 milliamperes, enters C1, and the other 75 milliamperes enters C2. At t equals 1.5 milliseconds, the total current draw of 73.6 milliamperes splits into 2 equal paths, 36.8 milliamperes entering C1, and an equal amount of 36.8 milliamperes entering C2. At t equals roughly 3 milliseconds, the total current draw of 36 milliamperes splits into 2 equal paths, 18 milliamperes entering C1, and the remaining 18 milliamperes entering C2. Finally, at t equals 10.5 milliseconds, the charge process is complete, current flow ceases, and neither capacitor in the identical parallel arrangement draws current. At any point in time, an application of Kirchhoff's current law demonstrates that current into the total capacitance will be the summation of current through the individual capacitors comprising the parallel arrangement. I total equals I1 plus I2. Given equal capacitors in parallel, current splits evenly between them. For this parallel arrangement of equal capacitors, you could express voltage across C1 as V1 of t equals 15.8 volts times 1 minus e to the negative t over 2.1 milliseconds. Voltage across C2 is V2 of t equals 15.8 volts times 1 minus e to the negative t over 2.1 milliseconds. Current through C1 is I1 of t equals 75 milliamperes times e to the negative t over 2.1 milliseconds. and current through C2 as I2 of t equals 75 milliamperes times e to the negative t over 2.1 milliseconds. At any time, voltage across these identical parallel elements is the same, and current divides equally. Option 3. Also super easy. The elements inside the box are a series arrangement of identical capacitors that happens to yield a total capacitance of 20 microfarads. Consider a series arrangement of two 40 microfarad capacitors yielding a total capacitance of 20 microfarads. Given current through elements in series is the same, current through C1 and current through C2 will be the same at any point in our analysis. I1 equals I2, which equals the current through the total capacitance from our previous analyses. Current through elements in series is the same. At t equals 0, both capacitors experience an initial surge of 150 milliamperes. By 1.5 milliseconds, both capacitors experience 73.6 milliamperes of current. By roughly 3 milliseconds, both capacitors experience 36 milliamperes of current. And finally, at t equals 10.5 milliseconds, the end of the charging process, both capacitors are fully charged and current flow will have ceased. Let's now examine how voltage distributes itself inside this series arrangement of identical capacitors. Given these identical capacitors experience identical rate of charge transfer, i.e. current, throughout the charging process, the charge inside either capacitor at any point in the charge process will be the same. Given the relationship of capacitance equals charge over voltage, identical charge, whatever it might be, and an identical capacitance, in this case 40 microfarads, yields an identical voltage. In an occasion of identical capacitors in series, voltage is split evenly among the capacitors forming the series relationship. For this series relationship comprised of two identical capacitors, at any point in time, half the voltage experienced by the total capacitance will be dropped across C1, and the other half will be dropped across C2. At t equals 0, both capacitors are initially uncharged at 0 volts. By 1.5 milliseconds, C1 will have charged up to half of roughly 8 volts, or 4 volts, as will C2. By roughly 3 milliseconds, C1 will have charged up to half of 12 volts, or 6 volts, as will have C2. And finally, at 10.5 milliseconds, C1 will have charged up to half of 15.8 volts, or roughly 7.9 volts, as will have C2. At any point in time, an application of Kirchhoff's voltage law demonstrates that the voltage across the total capacitance will be the summation of the individual capacitors comprising the series arrangement. V total equals V1 plus V2. Given equal capacitors in series, voltage is apportioned evenly between them. For the series arrangement of equal capacitors, you could express voltage across C1 as V1 of t equals 7.9 volts times 1 minus e to the negative t over 2.1 milliseconds. Voltage across C2 as V2 of t equals 7.9 volts times 1 minus e to the negative t over 2.1 milliseconds. Current through C1 as I1 of t equals 150 milliamperes times e to the negative t over 2.1 milliseconds. And current through C2 as I2 of t equals 150 milliamperes times e to the negative t over 2.1 milliseconds. At any time, current through these series elements is the same, and voltage is apportioned equally. Option 4 and Option 5, not so easy. Option 4 is a parallel arrangement of unequal capacitors, and Option 5 is a series arrangement of unequal capacitors. Let's use a different, more simplified setup to explore these two options one at a time. Starting with Option 4, a parallel arrangement of unequal capacitors. This is where you kind of need to pay attention because it's about to get weird.